So we have completed the density of crystal. I have already sent some assignments for you, the numericals. I hope you have completed it. If you have any doubt, you can ask me. Now next we go to the imperfections in solids. That is defects in solids. Imperfections in solids. In solids or defects in solids. See, we have already learned that the crystalline solids have a perfect ordered arrangement. But this perfect ordered arrangement can be seen only at absolute zero temperature, that is at the lowest possible temperature. Then only these particles will be having a perfect ordered arrangement. When temperature rises, the disorderliness will increase, that is these molecules, these crystals, they will lose their perfect ordered arrangement. Such deviation from the perfect ordered arrangement is called the imperfections in solids. See, sometimes the imperfections or defects can be seen at certain points or lattice sites. Then we call them as point defects. So we have point defects, or sometimes it will be along a line, particular line there will be the defects. Then we call them as line defects. Line defects. So it can be point defects or line defects. So the ordered arrangement will not be there. Now actually the defects are mainly classified into two types. They are stoichiometric defects and non-stoichiometric defects. Stoichiometric defects and non-stoichiometric defects. Now, what is stoichiometry? Stoichiometry is the perfect or the definite fixed ratio present between the atoms of the elements in a compound. So those defects which affect the stoichiometric ratio of the compound, which do not affect, they are called stoichiometric defects, and those which affect the stoichiometric, they are called non-stoichiometric defects. That is, after that, if the defects is there, they will become non-stoichiometric because that perfect fixed ratio will not be there in that compound when the defects are formed. Here, even after the defects are formed, that stoichiometric ratio will be kept. So that is why those defects are called stoichiometric defects, and the defects which affect the stoichiometric defect ratio are called non-stoichiometric defects. ചില ഡിഫക്ട്സുകൾ ഈ ഫിക്സഡ് റേഷ്യോനെ യാതൊരു തരത്തിലും ബാധിക്കില്ല. ഇറ്റ് വിൽ നോട്ട് എഫക്റ്റ്. ആ പെർഫെക്റ്റ് ഫിക്സഡ് റേഷ്യോ വിൽ ബി ദർ. അപ്പോൾ അങ്ങനത്തെ ഡിഫക്ട്സിനെ നമ്മൾ എന്ത് പറയും? സ്റ്റോയിഷ്യോമെട്രിക് ഡിഫക്ട്സ് എന്നും. Those defects that affect that stoichiometric ratio. Stoichiometric ratio, what is stoichiometric? For example, water is 2. We have this 2:1. Number of atoms of hydrogen and oxygen is in the ratio 2:1. In sodium chloride, it is 1:1. The fixed ratio is followed. KCl, it is 1:1. So this fixed ratio will be affected if such defects are there. Such defects are called non-stoichiometric defects. Now we go in detail about the stoichiometric defects. Stoichiometric defects. Now there are different types of stoichiometric defects. See, those crystals we have in the constant particles can be either atoms or ions, etc. So this type of stoichiometric defects, there are two types. They are called those affect non-ionic solids. The defects which affect the non-ionic solid, or the defects, stoichiometric defects that is present in non-ionic solids. And in ionic solids. In ionic solids. So these are the two different types. So the stoichiometric defects can be either seen in non-ionic solids, that is solids which are either made up of atoms, neutral atoms. Then in in ionic solids, the solids which are like sodium chloride, potassium chloride, silver bromide, etc. So we'll come to the defects which affect the non-ionic solids. The first type is vacancy defect. Vacancy defect. Vacancy defect means the atoms which are to be occupying the lattice sites, they will be absent from the site. Those atoms which must be there, that atoms will not be there. So the vacant site is unoccupied, or the vacant sites are left unoccupied. That type of defect is called a vacancy defect. Suppose one atom like this is all solid, and here there is an atom, and this is the site where the atoms are occupying. If an atom is not occupying its site, then we call it as, see, this site is not occupied, so we call it as a vacancy defect. And this vacancy defect decrease, due to vacancy defect, the density of the crystal will decrease, because some atoms are not there, so mass per unit volume will be less. So due to vacancy defect, the density will decrease. Now next is interstitial defect. Interstitial defect. See, in interstitial defect, what happens is the atoms, some atoms will be occupying the interstitial site. In addition to the normal site, they will be occupying the interstitial site also. Like this, if it is the sites, these are like this. These are the sites occupied. This is the lattice site. The atoms will occupy the lattice site also. In addition to the interstitial site, in addition to the normal lattice site, they will occupy the interstitial site also. Such defects are called interstitial defects. So we have these two type of defects in non-ionic solids. That is the vacancy defect, which will decrease the density of the crystal. What about the interstitial defect? Mass per unit volume will increase, so that will increase the density. So due to interstitial defect, the density will increase. So vacancy defect and interstitial defect is seen in non-ionic crystals. So non-ionic crystals will show these two types of defect. That is vacancy defect, which will decrease the density of the crystal, and the interstitial defect that will increase the density of the crystal. Now we will go to those defects which affect the ionic solids. First one is Schottky defect. Schottky defect. Now what is Schottky defect? This type of defect is shown by ionic solids. Ionic solids are made up of positively and negatively charged ions. They will be made up of positively charged and negatively charged ions. Positive charged ion, negatively charged ion, like this. This is negatively charged. Like this. Now here, what happens is, some lattice site will be vacant. Some lattice site will be vacant. See, here the lattice site is vacant. This lattice site is vacant. This lattice site is also vacant. See here, this lattice site is vacant, which must be occupied by the positive charge that lattice site is vacant. Here another lattice site is vacant. That is here this will here there must be a negative charge. So this type of defect is called a Schottky defect. Understood? So this is Schottky defect. But number of the cation vacancies will be equal to number of anion vacancies. Therefore, the cation, since the cation vacancy is equal to anion vacancy, the crystal as a whole will be neutral. There will not be any charge for the crystal. The crystal as a whole, it will be neutral because the number of cation vacancies is equal to number of anion vacancies. This is Schottky defect. It is shown by crystals whose coordination number is very high, like the sodium chloride, potassium chloride, etc. The coordination number is very high. What is coordination number? The number of immediate neighbors. That is called the coordination number. So this type of defect is shown by compounds whose or ionic compounds where the ions show high coordination number, and also there is a they almost have similar sizes. So this type of defects are shown. This type of defects is shown by compounds which have high coordination number, and the size of the cation and anion are almost the same. This is Schottky defect, and due to Schottky defect, see what is happening. The cation and anion is missing from the lattice side. That means the mass per unit volume will decrease. So after Schottky, since the Schottky defect, if it is there in a crystal, that will decrease the density of the crystal. So this is Schottky defect. Now next type of defect is Frankel defect. Frankel defect. In Frankel defect, the lattice site will be vacant, but the positive ions which are present in the lattice site, instead of lattice site, they will be present in the interstitial site. Instead of occupying the actual site, they will occupy the interstitial site. That is the only difference. That is, here positive ion will be occupying here. It's not occupying here, but it is occupying the interstitial site. Usually cations will go to the interstitial site because they have smaller size. So that is Frankel defect. So in Frankel defect, the cations which must occupy the lattice site, instead of occupying the lattice site, they will go and occupy the interstitial site. Such type of a defect is called a Frankel defect. And in Frankel defect, the Frankel defect is shown by crystals whose coordination number is very low. If coordination number is very low, then they will show this type of Frankel defect. And if the cation and anion, their size are there is a large difference between the size of the cation and anion, then they will show the Frankel defect. So the ionic defects shown by ionic compound show this type of two defect, that is Schottky defect and Frankel defect. In Schottky defect, the cation and anions will be missing from their lattice site, and number of cation vacancies will be equal to number of anion vacancies. Therefore, it will not change the neutrality of the crystal. The crystal as a whole will be neutral, but the mass per unit volume will decrease. Therefore, density will decrease. But in Frankel defect, instead of occupying the lattice site, the cation will occupy the interstitial site. The cation will occupy the interstitial site, and therefore charge as a whole will be neutral, but that there is no change in the density because there is no change in the mass. Therefore, the density will be the same. So in Frankel defect, there is no change in density, but in Schottky defect, the density will decrease. Now, the Schottky defect is shown by crystals whose coordination number is very high, whereas Frankel defect is shown by crystals whose coordination number is very low. Then Schottky defect is shown by crystals where the cation and anionic sizes are almost the same, whereas in Frankel defect, the cation and anion size, if there is a large difference, then only the Frankel defect can be shown. And there is only one crystal who show both this defect, that is the Schottky and Frankel defect, that is silver bromide, AgBr. It shows both both the frontal and Schottky defect. Certain places it is showing the frontal defect and certain parts it is showing the Schottky defect. So this is about the stoichiometric defects. Now we will go to non-stoichiometric defects. Now non-stoichiometric defects are of two different types. They are mental deficiency defects and mental excess defects. First one is mental excess defect. Mental excess defect or mental deficiency defect. But first we will take mental excess defect. See, when anions are absent from the lattice site, then metal ions will be excess, isn't it? So, and if anions, if they are absent from the lattice site, they will lose their electrical neutrality. But to keep the electrical neutrality, that site will be occupied by electrons. So, such type of defects. So, anions are missing, but that site occupied by the anions will be occupied by an electron. So, charge will be neutral, but the percentage of the mass of cation or the metal will be high. That is called a metal excess defect. And due to this metal excess defect, the stoichiometric ratio of the crystal is affected. Now, this type of metal excess defect is shown by alkali metal halides. Alkali metal halides means potassium chloride, sodium chloride, lithium chloride, potassium bromide, sodium bromide, etc. So, the alkali metals, that is first group metals, when they react with the 17th group nonmetals, that is very strong nonmetals, they form ionic compounds. Those alkali metal halides, they show this type of metal excess defects. See, when sodium chloride is heated with in the presence of sodium vapor, the crystal will turn yellow. Why the crystal is turning yellow? See, the surface, the sodium chloride contains sodium ions. Sodium ions and chloride ions will be there in the crystal. Sodium ions and chloride ions will be there in the crystal. Now, when it is heated in presence of sodium vapor, what happens is sodium atoms get attached to the surface of the crystal. Sodium atoms, because sodium vapor contains sodium atoms, sodium atoms will come and attach on the surface of the crystal. Then what happens is the chloride ions from the bulk, the chloride ions will move to the surface, diffuse to the surface to react with the sodium atom. Then what happens is chloride ions will come to the halide ions will come to the surface to react with the alkali metal atom. Alkali metal atom, when it reacts, it loses one electron. And this electron is there. So sodium ions will combine with the chloride ions which came to the surface, and this electron which is formed there will diffuse back and occupy the position occupied by the chloride ion. So now the metal is in excess, but it is electrically neutral because that negative charge is given by the electron. This type is a metal excess defect, and this site which is occupied by the electron is called an F center. It is called an F center, and due to this F center, the crystal is being colored. So that is why sodium chloride, when it is heated with the sodium vapor, it becomes yellow in color, because this chloride ions from the bulk will move to the surface to react with the sodium atoms. Then the electrons which are formed during the reaction will diffuse back, and they will occupy the site which were occupied by the halide ions, and that site which is occupied by the electron is called an F center. Now F centers are formed. Due to F centers, the crystal will become colored. This is metal excess defect. Now potassium chloride, if you heat, it will become violet in color. Lithium chloride, if it is heat with the lithium vapor, it will get a pink color. So the different colors will be there. So this is metal excess defect, one type. Another type, when zinc oxide. When zinc oxide is heated, it is made up of zinc ions and oxide ions. Oxide ions. This, it will lose oxygen when it is heated. So zinc oxide, when you heat, you will get Zn2 plus half O2 plus 2 electrons. These electrons will occupy the interstitial site or the site occupied by the oxygen also, and zinc ions which are excess, they will go and occupy the lattice site, sorry, interstitial site. Therefore, what happens is the zinc ion became excess and the zinc oxide, it will become yellow in color. So now zinc ion, when it is in excess, oxygen, oxide ion will lost as oxygen gas. Therefore, zinc ion is excess. Therefore, it is a metal excess defect. So these are two different types of metal excess defects. Now there is metal deficiency defect that will come. We'll talk about it in the next class.